Welcome to RenEnergy.com, your renewable energy and sustainability platform. Hello, and welcome to the RenEnergy.com YouTube channel, where we're dedicated to exploring the transformative power of green hydrogen technologies. We investigate the cutting-edge advancements, real-world applications, and the future potential that green hydrogen holds. In today's episode, we're focusing on how this incredible technology is reshaping the train industry. So sit back and get ready to discover the world of green hydrogen with us. Background of the train industry. The train industry has been a fundamental part of global transportation infrastructure for over a century. With extensive networks connecting cities and countries, trains have facilitated commerce, tourism, and daily commuting. Historically, the train industry has relied on fossil fuels, especially diesel, to power locomotives. This has allowed for robust and efficient travel but has also contributed to environmental concerns, including carbon emissions and air pollution. The importance of decarbonization. In the face of climate change and mounting pressure to reduce greenhouse gas emissions, the need for decarbonizing the train industry has become paramount. Decarbonization refers to the process of reducing or completely eliminating carbon emissions, particularly from fossil fuel combustion. For the train industry, this means transitioning from traditional fuels to cleaner and more sustainable energy sources. Such a shift is vital not only for mitigating the industry's environmental impact but also for aligning with global climate targets and regulations. Green hydrogen, an overview. Definition and production methods. Green hydrogen refers to hydrogen fuel that is produced using renewable energy sources, such as wind, solar, or hydroelectric power. Unlike traditional hydrogen production methods that often rely on fossil fuels, green hydrogen's production involves the electrolysis of water, splitting it into hydrogen and oxygen. This process can be completely carbon-free if powered by renewable energy. There are several production methods for green hydrogen. Alkaline electrolysis. This method uses an alkaline solution as an electrolyte and is considered a well-established technology. Proton exchange membrane PEM electrolysis. This method uses a solid polymer as an electrolyte and is known for its high efficiency. Solid oxide electrolysis. This is an emerging technology that operates at high temperatures, providing potential efficiency gains. Benefits and challenges. Benefits. Environmental sustainability. Green hydrogen produces zero carbon emissions when generated using renewable energy, aligning with global efforts to combat climate change. Versatility. It can be used in various applications, from transportation to power generation, offering flexibility within the energy system. Energy storage. Green hydrogen can be stored and transported, providing potential solutions for energy balancing and grid stability. Challenges. High costs. Current production technologies can be expensive, particularly in comparison to traditional fossil fuels. Infrastructure requirements. Wide-scale adoption of green hydrogen requires significant infrastructure development, including refueling stations, pipelines, and more. Efficiency concerns. Energy losses during production. Current state of the train industry. Traditional fuels and technologies. The train industry has historically been dependent on fossil fuels such as diesel and coal. These traditional fuels have been used to power locomotives, providing a reliable source of energy. Diesel engines, in particular, have been the mainstay of the train industry, renowned for their efficiency and power output. However, these traditional fuels and technologies have also been associated with substantial greenhouse gas emissions, pollution, and other environmental concerns. Environmental impact. The reliance on fossil fuels has significant environmental implications for the train industry. Carbon emissions. Burning fossil fuels releases large quantities of carbon dioxide, contributing to global warming and climate change. Air pollution. Diesel engines emit pollutants like nitrogen oxides and particulate matter, which have harmful effects on air quality and human health. Resource depletion. Dependence on non-renewable fossil fuels raises concerns about long-term sustainability and the potential impacts of resource scarcity. While efforts have been made to mitigate these impacts, such as implementing emission controls and improving fuel efficiency, the fundamental environmental challenges associated with fossil fuel reliance remain. Regulation and policy landscape. The regulatory environment surrounding the train industry reflects growing awareness of the need to reduce environmental impacts. Emission standards. Many countries have established emission standards to limit pollutants from locomotives, pushing the industry towards cleaner technologies. Climate agreements. International climate agreements like the Paris Agreement have set targets for reducing greenhouse gas emissions, influencing national policies affecting the train industry. Incentives for innovation. Governments are increasingly providing incentives, grants, and support for research and development in cleaner transportation technologies, including electrification and hydrogen fuel cells. The policy landscape is increasingly shaping the industry's trajectory, with a growing focus on sustainability, innovation, and decarbonization. Regulations are not only driving the adoption of cleaner technologies but also encouraging broader systemic changes within the industry. Green hydrogen in the train industry. Feasibility and potential applications. Green hydrogen presents a promising opportunity to decarbonize the train industry. Its feasibility largely depends on technological advancements, cost reduction, and infrastructure development. The potential applications include hydrogen-powered locomotives. Hydrogen can be used as a fuel in trains either through fuel cells that convert hydrogen into electricity or directly in hydrogen combustion engines. Energy storage and grid integration. Green hydrogen can act as a flexible energy storage medium, allowing better integration of renewable energy sources into railway power systems. Hydrogen-based hybrid systems. Combining hydrogen with batteries or other energy systems can create hybrid solutions that offer improved efficiency and flexibility. Case studies and real-world implementations. Several projects and real-world implementations highlight the potential of green hydrogen in the train industry. Germany's hydrogen trains. Germany has been a pioneer in deploying hydrogen-powered trains, with the Coradia I-Lint being the first hydrogen fuel cell passenger train in operation. United Kingdom's HydroFlex project. This project involved converting a traditional train to run on hydrogen fuel cells, demonstrating the feasibility of retrofitting existing rolling stock. California's hydrogen fuel cell locomotives. Efforts in California to develop and test hydrogen-powered locomotives for freight transportation show the potential for heavy-duty applications. Technological considerations. For green hydrogen to become a significant part of the train industry, several technological considerations must be addressed. Fuel cell efficiency and durability. Ongoing research and development are needed to improve the lifespan and efficiency of hydrogen fuel cells. Infrastructure development. Building hydrogen refueling stations, pipelines, and other essential infrastructure is crucial for wide-scale adoption. Integration with existing systems. Successful integration of hydrogen technologies with existing rail systems and operations will require careful planning, standardization, and collaboration across the industry. Safety and regulations. Ensuring safe handling, storage, and transport of hydrogen will necessitate comprehensive regulations and training. Economic analysis. Cost of green hydrogen production. The cost of green hydrogen production is a critical factor in its adoption within the train industry. Factors affecting the cost include electricity prices. Since green hydrogen production involves electrolysis, the cost of electricity, preferably from renewable sources, is a significant component. Technology and scale. The choice of electrolysis technology and the scale of production can influence costs. Larger production facilities often benefit from economies of scale. Infrastructure investment. The development of necessary infrastructure such as refueling stations and distribution networks adds to the overall cost. While costs have been decreasing with technological advancements and increased production, green hydrogen still generally remains more expensive than traditional fossil fuels. Financial incentives and support. Governments and organizations are recognizing the potential of green hydrogen and are offering various financial incentives and support to foster its growth. Grants and subsidies. Many countries provide grants, subsidies, or tax incentives to support the research, development, and deployment of hydrogen technologies. Public-private partnerships. Collaborations between public entities and private industry can help share risks and leverage investments in green hydrogen projects. International funding. Global initiatives and organizations may provide funding for projects that align with climate goals and sustainable development. Such financial support is vital for overcoming the initial economic barriers and driving the adoption of green hydrogen in the train industry. Comparative analysis with other renewable sources. Green hydrogen must also be considered in the context of other renewable energy options. Electricity from renewables. Direct electrification using renewable energy, for example, wind, solar, may offer a more efficient pathway in some applications. Biofuels. Renewable biofuels provide another alternative for decarbonizing the train industry but come with their own cost, sustainability, and availability considerations. Battery technology. Battery electric trains offer a competitive option, with costs depending on battery prices, energy density, and charging infrastructure. Comparing green hydrogen with these alternatives requires a comprehensive analysis considering not just costs, but also efficiency, environmental impact, scalability, and integration with existing systems. Environmental and social implications. Reduction in greenhouse gas emissions. the adoption of green hydrogen in the train industry offers significant potential for reducing greenhouse gas emissions. Carbon neutrality: when produced using renewable energy, green hydrogen does not emit carbon dioxide during its production or consumption, contributing to carbon neutral operations. Reduction of other pollutants: besides carbon emissions, hydrogen-powered trains also reduce emissions of other harmful pollutants like nitrogen oxides and particulates, improving air quality. Impact on communities and employment: green hydrogen's emergence in the train industry could have substantial effects on local communities and employment. Job creation: investment in green hydrogen technologies and infrastructure can create new jobs in manufacturing, construction, research, and maintenance. Transition challenges: a shift from traditional fuels may also lead to job displacement in existing industries, necessitating retraining and support for affected workers. Community engagement: transparent engagement with communities about changes and potential benefits can foster acceptance and collaboration. Considerations for sustainability: the sustainable integration of green hydrogen into the train industry involves several considerations. Resource utilization: the production of green hydrogen must ensure responsible use of water and other natural resources. Energy source: the environmental benefits depend on using renewable energy for hydrogen production, as non-renewable methods negate some of the emission reduction gains. Life cycle analysis: a comprehensive assessment of the entire life cycle of green hydrogen technologies, including production, use, and disposal, ensures a holistic understanding of its sustainability. Alignment with broader goals: the integration of green hydrogen should align with broader environmental, social, and governance (ESG) goals to ensure that it contributes positively to societal well-being. Challenges and future directions. Technological challenges: the integration of green hydrogen into the train industry faces several technological challenges. Efficiency and performance: achieving efficiency levels that compete with existing diesel technologies is an ongoing challenge. Infrastructure development: creating a robust hydrogen distribution and refueling infrastructure is a complex and costly endeavor. Safety considerations: handling and storing hydrogen requires stringent safety measures, and standards must be developed and adhered to. Integration with existing systems: retrofitting current trains and infrastructure to accommodate hydrogen technology presents technical challenges. Policy and regulatory barriers. Policy and regulatory factors can either facilitate or hinder the adoption of green hydrogen. Lack of coherent policies: inconsistent or conflicting policies across regions can create uncertainty and hamper investment. Regulatory approval processes: lengthy and complex approval processes for new technologies can slow down development and implementation. International coordination: harmonizing regulations and standards across countries would support a more seamless global adoption of green hydrogen in trains. Future trends and research needs. The future of green hydrogen in the train industry will likely be shaped by several trends and research directions. Increased investment in R&D, ongoing research and development will be crucial for overcoming technical barriers and reducing costs. Public-private partnerships, collaborations between governments, industries, and academia will foster innovation and facilitate commercialization. Global policy alignment: a coordinated global approach to policies and incentives can accelerate the transition to green hydrogen. Focus on sustainability: ensuring that green hydrogen is produced and used in a manner that aligns with broader sustainability goals will be a continuous priority. Adoption in other sectors: the success of green hydrogen in other sectors, like automotive or industrial, might influence its adoption in the train industry. Case studies. Country/region specific implementations. Several countries and regions have embarked on projects to integrate green hydrogen into their train systems. Here are some notable examples. Germany: the Coradia I-Lint is the world's first hydrogen-powered passenger train, showcasing successful implementation and collaboration between government and industry. United Kingdom: the HydroFlex project represents a groundbreaking effort to retrofit existing trains with hydrogen fuel cells, offering a potential pathway for broader application. California, USA: in the freight sector, California's initiatives in developing hydrogen-powered locomotives indicate the technology's applicability beyond passenger transport. China's ambitious plans and investments in hydrogen infrastructure and technology, including trains, signal the country's commitment to a hydrogen economy. Lessons learned and best practices. From these and other case studies, several lessons and best practices emerge. Collaboration is key. Successful projects often involve partnerships between governments, industries, research institutions, and communities. Technology adaptation: tailoring technology to specific regional needs, regulations, and existing infrastructure can enhance success. Investment in infrastructure. Early investment in hydrogen refueling and distribution infrastructure is vital for supporting wider adoption. Public engagement. Transparent and inclusive public engagement can foster acceptance and smooth implementation. Conclusions. The case studies of green hydrogen in the train industry offer valuable insights into practical considerations, challenges, successes, and failures. They provide tangible evidence of the technology's feasibility and reveal key factors that can influence its successful integration. Summary of key findings. Feasibility of green hydrogen. Green hydrogen is not just a theoretical concept. Real-world implementations demonstrate its practicality in the train industry. Multifaceted considerations. Successful integration requires a balanced approach, considering technological, economic, environmental, social, policy, and regulatory aspects. Global interest and variation. Different countries and regions are exploring green hydrogen in trains, each with unique approaches and challenges. And there we have it, a comprehensive look at how green hydrogen is revolutionizing the train industry, offering cleaner and more sustainable solutions. If you're fascinated by green hydrogen technologies just like we are, please hit the like button, subscribe to our channel, and turn on notifications. For in-depth articles, studies, and all things green hydrogen, visit our website at renenergy.com. Together, we're driving innovation and building a brighter, greener future. Thank you for watching, and see you in the next video. Thank you for choosing renenergy.com as your go-to source for all things renewable energy and sustainability. With our YouTube channel, we explore the latest developments and innovations in the field, including hydrogen fuel cells and the use of AI and machine learning to optimize energy consumption. If you're ready to take the next step towards a cleaner, more sustainable future, visit us at renenergy.com and discover the many ways we can help you transition to renewable energy. Thank you for watching and subscribing. Stay up to date on all the latest news and insights by subscribing today.